Hello everyone. Welcome to today's session. We'll start our session from where we have ended the last time. So in our course Fluid Dynamics for Astrophysics. Last time we discussed about various properties and the sample assignment problems. So I hope you all having a good time with this course. So let's start. I will wait for some time for anyone if they have any doubt. Okay. So okay. So, last time I have answered some of your doubts from the group. This time, try to do the same. Oh, hello. Yeah. Okay, so let's start. Let me share my screen from where I have started the last time. So, as you can see, last time we have talked about the circulation vector, Kelvin's vorticity theorem, that is valid for inviscid and incompressible barotropic fluids. So we have derived this equation. So omega is the vorticity. This is from the Stokes divergence theorem. And then so we have discussed everything in this. Then we talked about the sample. Talked about the sample assignment problems, right? Yeah. So question number one was that this. So I'll give you some time to digest. So these are very simple, given that give a little time to recap the things about this. So this is very simple, right? I have given the answer for you so that you can check with yours. The fluid has to be invested in compressible and rotational. Secondly, I talked about this and how you can calculate the force. This is just a simple Newton's second law, as you see how the velocity changes, and the conservation equation is this Bernoulli's theorem. The total energy is constant. This will total energy, right? The pressure and the kinetic one. And then I talked about this on the character statement that viscosity will produce circulation fluids. I think I discussed about this. But, Okay, then yeah. So this you all have done, right? 4 and 5. 4 is just the mutual screw with the momentum equation. It will stick to the surface. Okay. Consider an inviscid monatomic ideal gas 1 mole. The specific enthalpy of the gas will be, so as the formula suggests, last time I told you, but this I haven't told you, no? But no one have objected till now. So I think I left there somewhere. No. So let's get back to some of the more assignment questions. Okay. So the first question was, consider a smooth sphere immersed in a fluid that is steadily flowing past it in the positive direction at a speed u. As per an observer standing in the lab, there are no temporal changes in the flow. So temporal changes mean changes in time. So the partial derivative in time is tends to 0. Select the statement that are correct. So the first statement is reading like this: if the flow is perfectly inviscid, the tangential normal components of fluid velocity at the surface of the sphere are 0. Inviscid means, you understand, right? There is no viscosity. If the fluid viscous, the tangential and normal components of fluid velocity at the surface of the sphere is 0. So the question is related to the fluid velocity at the surface. If the fluid is perfectly inviscid, the fluid velocity u can be expressed in terms of the gradient of scalar potential phi, so that you can be expressed as minus of grad phi. If the flow is viscous and incompressible, the fluid velocity u can be related to the Laplace equation involving the velocity potential phi, L square phi is equal to 0 with the appropriate boundary conditions. So I'll give you some hint. As you already have done the assignments, I will still give you a hint, some hint that you can think of it. Like, uh, so it talked about the fluid is in a smooth sphere, smooth sphere that is immersed in the fluid, and the fluid is flowing in the positive x direction. The velocity given as u. So you are looking from the lab perspective, lab frame. So there are no timely changes of the flow. So the fluid is steadily flowing. Okay. I mean, yeah. So the delta is 0. So which will be the valid answer? Considering the fluid is inviscid and viscous. So I have already discussed with the Kelvin's volticity theorem and the Bernoulli's theorem. So you can think from those perspective. I'll give you some time to think. So uh, So let me give you the answer. So okay, so I have okay. So the flow is invisible. So first take the situation where the flow is invisible. So there is no viscosity. So in the Stokes equation, the viscous term is absent, right? And the momentum equation only contains part derivative of the fluid velocity. So therefore only one boundary condition is required on the surface of the sphere. So, okay, because uh, first derivative. So for the first derivative, there will come only one constant, only one boundary condition. So that's why it will be required. So um, see the fluid velocity you can explain in terms of the gradient of its fluid potential. So that IDS U is equal to minus grade phi. For the viscous flow, we need two boundary conditions. I think I have explained this earlier also. And the most commonly used boundary conditions require the fluid to stick on the surface of the sphere so that both normal and tangential components are zero. Okay. So option B. If the fluid inviscid, it's irrotational. Okay, so that curl of U is zero. So curl of U thought can be expressed as a some gradient. Gradient will be zero. For viscous flow, this is not valid. Yeah, for viscous flow, is not valid because the curl of U won't be zero. So the condition incompressibility is not relevant for this. If it is valid for incompressible, so incompressible means just that del dot U will be zero, right? So you can be related to the Laplace equation, which version no, this won't be valid. So option B and C are the right options. Just let me know how many of you have got this right. So so I think we have understood why options B and C are the right options. If you don't, please let me know in the group section, or you can also comment on the YouTube video after I upload this. So there also you can get in touch with me. So let's move on to the next question. Okay, so I may have slightly uh, shuffled the questions. So you see now the option question number 4. So consider two Earth-like planets 1 and 2. Both the planets have isothermal hydrostatic atmosphere. The atmosphere temperatures on the two planets are T1 and T2. Both the planetary atmospheres are under the influence of a constant gravitational acceleration g. You can assume that both the atmospheres comprise of fully ionized hydrogen, one proton and one electron. In atmosphere on, let the length scale over which the density changes by a factor of E B alone. The same quantity for atmosphere 2 is L2. Mm, Last time.
It's 2 o'clock.
From here we'll move on to a little fast. Okay, so option says on both cases the density will decrease with the height from the surface. This so imagine the scenario that two planets are same like Earth-like planets. Okay, and the atmosphere are same, isothermal temperature is same, hydrostatic equilibrium, but the temperatures are different. Okay, so both the planetary atmosphere are under the influence of a constant gravitational energy. So fully and hydrogen is the same. Length is clear. The density changes by a factor of E, B, alone, and density changes. Okay, so the relation between the density. So what do you think? Which options will be correct? Option B and D, you can think that L1 by L2. So simply L1 T1 is equal to L2 T2. So LT is constant. So L proportional to 1 by T. That means option B is length is inversely proportional to the temperature. And option D is length is directly proportional to the temperature. So which one it should be? So more the temperature, more the temperature gradient, right? So let's give to the answer. So we know the pressure gradient. Simply, pressure is rho gh. So from that we know that dp d to dp dk is minus rho g as uh, direction is altered. So more the length will go upper, the density will decrease, pressure will decrease. Sorry, pressure will decrease. So that so this is so you can see that rho is equal to 1 by z, right? Not that. And P is equal to this rho by mp kt. So if we replace P with this, we'll get that rho by mp, mp forget mp, dp dz is dt dz, okay, and rho, sorry, temperature is constant, right? Okay, so d rho dz, and we'll get there the t 1 by t. So 1 by rho d rho dz is minus d by mp kt. Right, this rho will come there. So then it will get ln rho. So ln, so here you can see that the 1 by z and here 1 by t. So obviously L proportional to t. So L1 by L2 is T1 by T2. So option D is correct. Option A is in both cases the density will decrease with the height from the surface. This is obvious, right? As for Earth like atmosphere, it is valid that if we go further and further in the positive direction, I mean away from the Earth's surface, the density always decrease, right? And this says so. So option A and D are correct. So we go on to the next question. I think we have understood. Give some time to digest. So the next question is consider a circular pipe of diameter 2a filled with a various field. The axis of the pipe is oriented along the horizontal direction. Consider cylindrical coordinates so that r is equal to 0 denotes the axis of the pipe and r is equal to a denotes its surface. There is a uniform pressure gradient along the positive x direction applied to the field. Okay. So pick the statements that are correct. The fluid will accelerate in the positive x direction. The fluid will flow with an x-directed velocity given by uxr gxp minus r square by k square, or k is a constant. The fluid will flow with an x-directed velocity given by uxr k times a square minus r square, or k is a constant. The quantity dux dr is not equal to 0. Okay. So as you understand correctly this question, that the pipe is circular and the diameter is given to s. So radius is a. The axis of a pipe, okay, there's uniform pressure gradient along the positive x direction and depending x applied to the fluid. Statements that are correct. The fluid will accelerate in the positive x direction. The fluid will flow with an x-directed velocity given by uxr exp minus r square by k square, where k is a constant. The fluid will flow. Okay, okay. So you can read and understand the questions. Mm, so option B is saying the positive x velocity will be exponential. Option B is saying that it will be this form. And option D is saying it is non-zero. So here it is given that as r is equal to a, it can be 0. Here also r is equal to, so if we move to the, so and the fluid is viscous, right? So the pressure gradient force, sorry, pressure gradient force will be balanced by the viscous frictional force. There will be no net force on a fluid parcel. Statement A is clearly not correct. Both the statements B and C look right in that the fluid velocity is maximum at the center and decrease towards the pipe walls. However, the boundary conditions mandate that the fluid sticks at the boundary. So the fluid velocity goes to 0 at the walls. Option C agrees with this. So yeah, statement D is clearly right for a viscous fluid, obviously. As you know that for viscous fluid, Karloff is not 0. Option C or D are right option. Mm, Okay. Next question. Consider a smooth spherical ball of radius A falling through an infinite viscous medium under the influence of gravity. Intuition tells you that it will stop accelerating after some time and will attain a steady terminal velocity. By conducting experiments on balls with various radii, you observe that the terminal velocity is proportional to a square. So all the balls are made of the same material, so that their densities are the same. So pick the correct statements. The drag force on the ball is proportional to A and proportional to its velocity. The drag force on the ball is proportional to A square and proportional to the square of its velocity. The terminal velocity attained because the drag force is equal and opposite to the gravitational force on the ball. So it is said that the ball is smooth and spherical and falling an infinite viscous medium. So the gravity will apply. The terminal velocity is said that is proportional to A square. Okay, that it is. So now the terminal velocity attains when something falls under the gravity, and the gravitational force will be balanced by its viscous force, so that it will attain a steady velocity and it won't accelerate anymore. So that is the terminal velocity. So as you can see in the diagram, okay, cylinder with viscous fluid flowing in positive direction. Okay, so the terminal velocity is reached when there is no force. Obviously, the drag force Fd is equal to gravitational force Fg. Okay, so gravitational force is proportional is mg, and that is proportional to rho a cube g. Okay, so then Fd. So suppose we take the drag force is proportional to a to the power p u to the power q. So it needs to match this. So u also proportional to u square. So you can get here p plus 2 get 3. So on the choice sheet, it will work only for p is equal to 1, q is equal to 1, right? And the drag force on the ball is proportional to n, proportional to its velocity. So simply, okay. Moving on to the next question, that consider an incompressible fluid flowing through a pipe. The pipe is horizontal, but its cross-sectional radius is not constant throughout its length. In section 1 of the pipe, its radius is 2 cm and the flow speed is 10 cm per second. In section 2 of the pipe, its radius is 5 cm. Sections 1 and 2 are joined smoothly, so there is no abrupt transition. Choose the correct answer. You can see option A, B, C, and D are given. Okay. So this is similar to this question, if you remember. Uh, but from mass conservation, we get that V1 A1 is equal to V2 A2. So V2 if on is on 0.6 centimeter per second. and that is less than p1, right? So from one is constant, we can get that p2 greater than p1. So option A and D are correct because the pressure in section 1 is less than pressure in section 2. And option A is fluid velocity in section 1 greater than fluid velocity in section 2. Right. Okay, so I'll give you some time here. I just So till now, I think everything is good. So, okay. So then, for next study. So to simplify food equations, we compare the contributions of various terms. Mach number. So you know the what is the Mach number is? Mach number is inertial term versus pressure gradient. Or it can also be defined as the velocity of a fluid divided by the velocity, the sound speed at that particular temperature. So in general, Mach number is defined as the initial term versus pressure gradient. How? So this V by Cs, V the velocity, Cs the sound speed, that is denoted by m. So we squared both sides, you'll get the V square by C square and m square. Initial term is rho dVdt, pressure gradient minus grad V. This is the del square V term with the rho nu, right? So rho nu, okay. So we know the viscosity is VL by nu. So we can then denote this term. This is the Reynolds number. Sorry, Reynolds number that is defined by the VL by nu. The initial term is viscous drag. This is the viscous drag. This is the pressure gradient. This is defined as the Reynolds number. Okay, so when is flow laminar? So when the flow will be laminar? So steady states, viscous force, zero acceleration, even seen turbulent flow of honey, low velocity, small characteristic length scales, but it shouldn't be too small, otherwise it can't be considered a fluid. So then you consider the flow to be laminar, right? When the flow is steady, so there will be no acceleration, so then it won't be turbulent. Turbulence is the opposite of laminar flow. So low Reynolds number is considered the laminar flow. When is flow turbulent? Inertial forces dominate over viscous drag. The initial force is of fluid that will dominate over the different viscous drag of the fluid. So then the flow won't remain as laminar, it will be turbulent. Chaotic flow is vortex shading, flow instabilities, as you all have this came across this in the lecture videos by Professor Prasad Subramanian. So then flow will be turbulent. Chaotic flow is basically the flow will be chaos. There will be chaos, like the flow is like moving arbitrarily in any direction. It is considered as chaos, and they often indulge with a high Reynolds number. Vortex setting is, you know, the when the vortex in the flow of fluid happen, when the uh, derivative of the flow, the double derivative will be zero. So there will be like saddle point kind of velocity. There will be the vortex setting. Flow instability is there will be instability in the flow. So then the flow is turbulent. Flow is called turbulent. Correspond to high Reynolds number. Plasma beta, gas pressure versus magnetic pressure. B field lines, rubber bands, magnetic field lines are frozen into plasma. Exert pressure when squeezed, stretched. Okay. That is the B field lines, rubber bands. So then magnetic Reynolds number. Reynolds number is also denoted to magnetic fields, and it is induction term versus diffusion term. We know the magnetic diffusion equation. You can just if you just simply uh, replace magnetic field with the velocity, it will get magnetic diffusion equation. Yeah, sorry, if you replace the density with the magnetic field, you will get the equation as del B del T, sub del O del T, Kala V cross B plus 1 by mu naught sigma del square B. This is a diffusion coefficient similar to the viscous coefficient. Acts the dissipation term, loss in B field. Okay. High Reynolds number is strong coupling of B fields with plasma. So higher number is the magnetic field is strongly coupled with plasma, so that they're not a separate quantity. They act together. Dynamic similarity in PTB theory, think of simpler unperturbed system. Read viscosity at a small perturbation. Use velocity scale of unperturbed system and its equation for static flows with no body force. Rho E dot grad U is equal to minus grad P plus mu del square U. Think of its solution as U is equal to U plus del U. Okay. I'll move a little fast because we have come across a lot of time and we're a little lagged behind. So U is velocity scale of unperturbed system and its equation for steady flows with no body force is rho E dot grad U minus grad P plus mu del square U. Okay. So if you replace x prime with x by L, the length is scale prime with the velocity. These are dimensionless quantity. So in this equation, in Stokes equation, you'll get that rho v square by L u prime. You will get this come across this u by L L u, and that is defined as Reynolds number, right? Rho u. So derive velocity vorticity equation for viscous barometric flux, and so that del omega del T is Carl P cross omega plus B del square omega. So this is the equation for the vorticity, and you will start with the velocity field rho del del T plus rho u dot grad u minus grad P plus mu del square u. Using u dot grad u is grad of half u square minus u cos Carl P. Rho del u del T will come across these terms. Taking Carl from the both sides, you will get Carl P is omega. So del omega del T. And the rho cancel out every side, this side, this side, this side. This will be grad P by rho because rho will be in the denominator. And this will again call up U is omega and E by rho will come across, yeah, E by rho, mu by rho, that is a nu by rho tropic fluids. And del omega del T will be simply this term plus this term, and this term will be 0 for barotropic fluids. So we'll see similar equation for the vorticity. Circulation not conjugate for inviscid flows. Why? The circulation K is not conjugate for inviscid flows. We know already this. So dissipative forces can set up vortices. Dissipative forces can set up vortices, right? So K is circular integration of U dot dl. So dk dt is du dt dot dl plus circular integration of d of half u square. Right. So redefine vorticity equation. X prime x by L, A prime A by U, omega prime is L by U omega. Why? Because to match the dimension, right? So L by U. What's the dimension of L by U? L by U is dimension of time, right? Because the dimension of omega dimension is U by L. U by L. So that's why L by U. Curl of U, right? So curl is 1 by L. So U by L, L by U. That's why this is this. Omega prime is this del prime plus U prime. This is L by U omega. L T is equal to X by U. So L by U X prime by U prime. Right. Over X by L. X is X prime L. U is U prime U. So L by U. So L by U time, and this is also time. So L by U T prime. So T prime will be U by L T, right? Del omega del 2, you get this already. So U by L, you just replace this. For T, you will get inverse of T, U by L del del 2. Just replace this. So take this as a homework and do this exercises. You will see. You'll come across this and you will see. Del omega prime del T prime is curl of E cross omega E prime cross omega prime plus R by RE. Del square prime omega prime. This is RE, not RE prime, remember. Because this is 1 by UL. UL, UU cancel out. So 1 by L cube. Yeah. So dimensionless quantities, scale sensitivity gone. Okay. So dynamic similarity, flow profile around two geometrically similar objects, scale version of same shape. The same BC and Reynolds number will be identical. Okay. So starting steady flows, dimensionless vorticity equation, and low Reynolds number. Contact with Stokes law. So del omega prime delta prime will be 0. Ignore for Reynolds number much less than 1. So it will get del prime of prime is 0. So two boundary conditions for viscous flow. Un is equal to U2 is equal to 0. Drag forces depend on many complex factors: shape of solid object in the fluid, orientation of solid object about the flow, so flow conditions, velocity, viscosity, length, scales of flow. Yeah. These will be flow conditions. So drag forces depend on many complex factors: shape of solid object in the fluid, orientation of solid object about the flow, flow conditions, velocity, viscosity, length, scales of flow. Many complex factors. Solid object in the fluid. Flow conditions. Yeah. So FD is steady, half of rho v square L square. Encapsulates all complex parameters, varies with shape, flow, etc. Usually found through experiments plotted against Reynolds number will reflect dependence on viscosity. Drag forces. FD CD half of rho v square L square. Is square L square. So then drag forces will be dependent on many complex factors. Shape of solid object in the fluid. We'll get this encapsulated complex parameters, values with shape, flow, etc. Usually found in experiments. Okay, we can get the value of CD from experiments. And Porter again Reynolds number reflect dependence on viscosity. For high Reynolds number flow, bulk flow effectively invisible. Okay, there will be no viscosity. High Reynolds number, low coefficient of viscosity, because Reynolds number is defined as only VL by nu. So low coefficient of viscosity. So viscosity will be ignored there, but does not imply low viscosity. Mu del U del Y. Viscosity is an important boundary object. This is the experimental kind of plot where this is the Reynolds number UMD by nu, and this is the CD. So you can see that CD is varies with the Reynolds number like this. High Reynolds number, CD will be low, about 1 and much less than 1. For low RE, equating FD, so we'll get PBX mu L mu, so half rho square square CD, so CD will be Rn by Re. Okay, so let's go on to the sample assignment problems. Consider a smooth solid metallic sphere moving through a fluid. The Reynolds number is 10 to the 4. So what are the correct options? The fluid will not stick to the surface of the body. The drag experienced by the sphere will be proportional to this square of the relative velocity between the sphere and the fluid. The total energy of the fluid will be exactly conserved along a streamline. The drag experienced by the sphere will be proportional to the relative velocity between the sphere and the fluid. So, so the correct answer will be B, because even though the Reynolds number is quite high, okay, as you can see the Reynolds number is 10 to the 4, so 10,000. There is still a small finite viscosity, as I explained here. That's why I have explained these slides for you. See, even for high RE flows, the coefficient of viscosity is low, but it does not imply low viscous stress. So that's why there is still a small finite viscosity because of which the flow will stick to the surface of the body. Okay. Since there will be some dissipation due to viscosity, option C cannot be true. That conserved along a streamline, no, total energy will be conserved because there will be dissipation due to viscosity. Whenever there is viscosity, the energy can be conserved. For a solid sphere moving through a high Reynolds number fluid, the drag will be proportional to v square. Okay, for v is the relative velocity between the body and fluid. Okay, so option B is the correct option. Question number 2. Consider a pipe of circular cross-section with a diameter 2a filled with the viscous fluid. Coefficient of viscosity is mu. The axis of the cylinder is along positive x. If the r is equal to 0 line passes through the center of the pipe, if the pressure gradient along the positive x is dp by a dot is equal to k, or k is constant, then for a steady flow, what are the correct options? So we have come across this earlier. The fluid will accelerate along positive direction. The shape of the x as a function of r will be Gaussian. Ux will be this form or this form. I think we have come across in the earlier assignment. The correct option is option C. So because the given yeah, the given the flow is u is x are 0 0. So in the body of x direction, pressure gradient will be dp dx is equal to k. Right? Yeah. So Navier-Stokes equation is said that rho del u del t plus rho u dot grad u minus grad p plus u mu del square. So dp dx is equal to mu by r d dr of r d mu dr is equal to k. So a simple integration, your will be r square 4 mu k plus a ln r plus b. So at u r is equal to a is equal to 0, it will be k square by 4 mu plus a ln a plus b. This equation will be 0 at r is equal to a. So then, and at r is equal to 0, it will be the u max. Okay. So 2 mu dr k r by 2 mu plus a by r is equal to 0. 0. So a is equal to 0. B is equal to k square 4 mu. So x will be k r square minus a square by mu. This option C. So you have already come up to this. This is like alternative of suggestion how to solve it. Question number 3. Choose the correct statement. The coefficient of viscosity related to the momentum flux. The coefficient of viscosity related to the heat flux. The shear stress tensor is stressless. The coefficient of thermal conductivity related to the heat flux. So this is about the heat and momentum flux. So the coefficient of viscosity related to which one? Momentum flux, heat flux. So you know already this related to the which flux. Shear stress tensor is testless. I told you testless means the trace, the diagonal, sum of the diagonal terms will be 0, the heat flux. So we know it is related to the momentum flux, obviously. Option B can't be right then. Shear stress tensor is testless because shear stress tensor is testless by definition. Okay. Finally, Q is equal to minus K grad T, K the coefficient thermal conductivity. Here to Q, the heat flux. So options A, C, and D are the right options. Assignment question number 4. Pardon me if I am moving a little fast. Consider a horizontal stream of very high Reynolds number, fluid hitting a vertical wall. Choose the correct option. The coefficient of viscosity mu is high, close to the wall. The coefficient of viscosity is quite small everywhere. But the term mu del square u, or the velocity, the nearest equation is important, significant near the wall. The term L omega by u is dimensionless, where L omega and u are characteristic length and velocity of the given system respectively. The coefficient viscosity is quite small everywhere. So which one is the right option? So in high Reynolds numbers,
It's 3 o'clock.
abbreviated by RE, mu is unimportant throughout the fluid, but mu del square u is important close to the wall because the flow comes to a stop and the wall and the velocity gradient are large. So del square u is large. Option C is correct one is to compute the dimensions. So if you L omega by u is dimensional, simply u is velocity, so length over time, L cancel out, time is there. Omega is again u by L. Obviously omega is u by L, L by u. So this is dimensional. Option C is correct. Option B is correct. Right. So these are some assignment problem. I think you have understood this. I have some more problems for you. You want to test outflow dynamics around an aeroplane wing using a geometrically similar miniature model in a wide tunnel. Or to do so, you would choose all correct option. If you want to test the flow dynamics around this. If the air in the wind tunnel is of exactly the same composition as it would be in the real life situation, it can't be right. Have the airflow speed over the miniature model so slower than it would be in real life. Not correct. Can be correct because the air is the wind tunnel of exactly the same composition as it would be in the real life situation. And the airflow speed over the miniature model faster than it would be in real life or the actual aeroplane wing. If the flow speeds in the wind tunnel are similar to those in the real life situation, choose a less viscous medium in the wind tunnel than the medium in which the actual airplane wing would operate. If the flow speeds in the wind tunnel are similar to those in the real life situation, choose a more viscous medium in the wind tunnel, medium in which the actual and wing would operate. You need to keep the Reynolds number constant. The size of the model is smaller than that of the actual airplane wing. Obviously, you just want to test. So the speed needs to be higher, the viscosity needs to be lower. So option B and C. Consider a flow for which the Reynolds number satisfies much less than 1, Mach number is much greater than 1. What is the correct option? This could represent the flow of a very viscous flow like honey. This is not right. It is much less than 1. The pressure gradient term, sorry, it can be because I are much less than 1. The pressure gradient term for such a flow is much less than the viscous term. So the correct option. Option is current pressure gradient is obviously much less than the viscous term. Plus in the denominator of the Reynolds number, or much less than 1 means viscosity is larger. So inertial term much less than viscous term, may much greater than 1. So inertial term much greater than pressure gradient term. It follows that the pressure gradient term is much less than 1. Option question number 3, we have seen that the viscous term in the momentum equation looks like rho nu del square u, and that the heating rate of the fluid due to viscous dissipation is rho nu del u by del xz square. Consider now a smooth solid sphere that is immersed in a fluid that is flowing past it. Reynolds number in the bulk flow That means parts of the flow that are far from the sphere is very large, but not infinite. So the bulk flow is invisible to a good approximation. What will be the correct options? Far away from the sphere, there will be invisible heating of the fluid due to viscous diffusion, right? At the surface of the sphere, the tangential velocity will be the same as that of the bulk flow. In other words, the fluid can have infinite tangential, if not possible. There will be appreciable various heating of the fluid in a thin boundary layer near the sphere. Correct. In the thin boundary layer near the sphere, the viscous term rho nu del square is comparable to the inertial term in the momentum equation. So, yeah, this is the correct option. The next question, we have seen that the drag force on a body in the low Reynolds number regimes goes at dl proportional to eta lu, where eta is the coefficient of dynamic viscosity, as we have discussed it earlier. L is the characteristic dimension of the body, and U is the characteristic fluid speed. This is Stokes' law. We have also seen that the drag force on the high Reynolds number region goes as dh proportional to rho e square L square, where rho is the fluid density. One typically plots the drag coefficient CD. It is equivalent to d by rho e square L square, a function of the Reynolds number. Now d can be dl or dh. Given this, pick the statements that are true. In the high Reynolds number regime, CD does not depend on the Reynolds number RE. We have shown you the plot. Remember that the CD is decreasing with the Reynolds number. In the low Reynolds number regime, CD proportional to RE inverse. In the low Reynolds number regime, CD does not depend on the Reynolds number. If the Reynolds number low, the total is equal to the high Reynolds number. It will underpin the drag. In the low Reynolds number regime, CD is equal to dl by rho e square L square, that is proportional to, is already given, CD is already given for rho. So dl dh also given proportional to rho e square by L square, proportional to eta by rho ul, proportional to 1 by re. So obviously B is the correct one. In the high re region, CD is dh by rho e square L square, has no RE dependence. So the CD versus RE plot will be a horizontal line for high RE. The RE inverse line is ordered from horizontal number will intersect this flat line and eventually go below it, so it will be interpret the drag. Okay, so option A, B and D. The next last question is, consider an object that is measures 30 meters along the x direction, 30 centimeter along the y direction, and 30 centimeter along the z direction. This question is in the context of the drag experienced by this object as it moves through a viscous fluid. We know that the drag depends upon the Reynolds number, which is defined as Re is equal to U L by nu, where U is the characteristic speed, L is the characteristic length, and U is the coefficient of kinematic viscosity. You can assume that the fluid is laminar and the drag is in the Stokes law regime. So this means that is correct. The object is moving in the x direction. The correct number to use for L would be 30 meter. X direction, the L would be 30 centimeter. If the object is moving in the y direction, correct number to use for L would be 30 centimeter. So the correct. In the context of drag, the relevant dimensions for L would be the one which is representative of the cross-sectional or frontal area that is represented to the floor. So for instance, if the object moves along this direction, the relevant dimensions would be y and or z dimension. So B and D. B, if the object is moving in this direction, the correct number to use for L would be 30 centimeter. And D is in the z direction, it will be 30 meter. Because for the drag, okay, for x, it will be y and z. So y and z is 30 centimeters. And for z, it will be x centimeter. So I think we've understood. If you have any doubt, let me know in the comment section or in the next session. So we'll be back. So this I want to discuss. I think this question is basically uh, to test your knowledge, basic understanding of the course, so that it will be beneficial to all of you. So for high Reynolds number, yeah, if you remember the plot, set low RE regime, this is owned by RE. So option B satisfies. In the high RE regime, CD is this. There is no RE dependence. Option A is correct. Option C can't be correct because low Reynolds number CD does not depend on saying. So it contradicts option B. So it can't be correct. Either option B or C will be correct. So, but option B is correct. So option C must be wrong. If you extrapolate, you see there is a dip in the high RE number. It corresponds to this one only. Option D. So these whole questions answer assignments are related to the understanding of the Reynolds number, and it will be low and high. Then simply I can help you that low Reynolds number means the fluid laminar, so there will be for viscous flow there will be high viscosity. For high RE, the fluid will be turbulent. So the role of viscosity is little. Okay. And basis in this is that. So that's how we came across these questions. And then again, just want to help you the understanding of these sounds. Any question, just let me know. Otherwise, we'll see each other next time. I'll end the meeting. Okay, have a good day and night. So these are all for now. So yeah. So I have a transcript for you. Anyway, okay, have a good day and night. So until we meet next time, I will again request you to please go through the video and the lecture notes. I have shared all of this for you. So you will find in the slides. So, uh, thank you. Good night.